you very much. And so continue. Yeah, so thank you very much for inviting me and to present our recent work. So this is a work with Shambhuta Bhattacharya. He was my old colleague there in Hong Kong. And so right now I booked just in Bielefeld, Germany, just 1 year ago. And so today we'll be talking about this it's a Calderon type problem, but it's for the higher order operator, in particular the Bi-Harmonic operator. And we'll try to determine the lower order coefficients up to the second order. And the second order term is governed by a second order tensor, and that is the crux of this talk. So let us begin with the Calderon problem. So we have seen several times. I just want to repeat one more time maybe. So we have this conductivity equation, which is a second order equation given in a bounded domain omega. So we have the conductivity gamma, and then we want to determine gamma inside omega or up to the boundary omega bar from the static voltage and current measurements at the boundary. And that is given by the Cauchy data of this problem, so which is U restricted at del omega and gamma tangent U restricted at del omega. And yes, we can determine gamma uniquely. And so for the 3 and higher dimension, this result is due to the seminal work of the Silvester and Ullmann. And also for 2-dimension case, this is true, and this is due to Nachman. But if the conductivity is anisotropic, so if the function gamma is not isotropic, so then the unique recovery assertion fails. So that was the thing we're just discussing a bit. So then you have the gauge invariance. So that means there exists a function which is diffeomorphic. So from omega to omega, fixing the boundary, and you do get 2 different conductivity for that. The boundary measurement is same, but they are different inside the domain. So with this, so we'll move into the second order equation. So the type of the second order equation. So what we deal in so far. So we have this Schrodinger equation. So for example, the conductivity equation can be reduced into a Schrodinger equation. So where this Laplacian is the leading part and the Q is the potential. And also you can reduce it into a first order, perturbed term. So we have the Laplacian operator plus a first order term. So that also we can do by reducing the conductivity equation. So for example, for the Schrodinger equation, so the question is same. So let's say we have minus a plus plus Q equals to 0 in omega, and then we measured the Dirichlet and Neumann data on the boundary. And from that information, we want to determine Q inside omega uniquely. And that we can do. So that's our result. And the next problem, so we consider that's the magnetic Schrodinger equation. So that is the D plus A whole square U plus QU. So where you can see this A is it's a magnetic field. So it's a vector field. And then we have also the scalar field Q, which is the potential. So now in this case, so we cannot determine Q and A uniquely. So we have the gauge invariance, it's a natural gauge invariance. So we have A equals to A plus grad phi. So that means if I have 2 A1 and A2, so I can recover A1 minus A2 up to some grad phi, and where the phi is a scalar function. So we can always say though the curl of A equals to curl of A1 equals to curl of A2. But we cannot determine A1 equals to A2. And of course, we can't determine the scalar part Q. So here is one example. So where, so this gauge invariance is matters. So that means if I have a second order operator with a first order perturbation, so then it's not really true that we can recover A uniquely as the first order term. So then we move into a part of Bi-Harmonic Operator. So this part of Bi-Harmonic Operator, you can see it's written. So it's a second order to fourth order operator. So it's elliptic equation, so it has to be even. So this is the fourth order operator. So we don't have any third order term, but we have a second order, first order, and zeroth order term. So the second order term here, so that is governed by a symmetric two tensor field. So that's a matrix. The AJK is the matrix. And this Bj, so this is a vector field, and this Q is a scalar field. This way. And so we'd be interested to know that if we define the Cauchy data associated to this problem, so then whether this Cauchy data determines this Q, B, or A, and A, or if it doesn't, then up to what we can determine, and so on and so forth. So I just want to mention like the physical motivation. So this this Bi-Harmonic operator, or in general this higher order operator, so that appears in the elasticity equations, for example, the buckling problem, or the Kirchhoff law plate equations. So where you can see that you do have this kind of this divergence. So this will give you Laplacian type, and then you have this grad square. So this will make you the fourth order equation. And in this plate equation, so then so this U represent this transversal displacement. B is the bending stiffness, and mu is the coefficient associated to Sleme parameters. So even if we assume these are isotropics, then we can formulate into some part of Bi-Harmonic operator. And there's one more example that I want to mention here. So it's a Penis-Branson operator in conformal geometry that is related to, I think, the cosmology of the supergravity stuff. It's quite new, I saw. And here, this equation looks kind of more appropriate to our problem. So here, they consider the space-time manifold, and or in general, any manifold we can consider. This is M, and this is the metric G. So we can also consider in Rn. So this is the we have the standard metric. So here is our the fourth order equation. That's the leading term, and then we have the second order perturbation. So because this divergence and D, these are the this will give you the second order perturbation, and then we have this will also give you some first order perturbation if we push it divergence here, and we have a zeroth order term. And so this QG or the AG, these are the terms related to the Q curvature, the scalar curvature, and the Ricci curvature. So now we are interested into the inverse problem, so that whether this associated Cauchy data recovers this Q, B, and A. So that's the problem we want to address. So we can define in two ways the Cauchy data. So it depends on how you're solving the problem. So if you solve the problem with the Navier data, so that means like U restricted on boundary, and then U restricted on boundary is given. And then we solve this Dirichlet problem. So this problem with this Dirichlet data, and then we define the Neumann data like this. So del square nu U and del Q nu U, so restricted on boundary. So that's one possibility. And another possibility is that we can also solve this Bi-Harmonic problem with this U restricted on del omega and minus the plus U restricted on del omega. And then the corresponding Neumann map would be that del U restricted on del omega, that's okay, and del U of minus the plus U restricted on del omega. So you can see that so comparing two different cases, Navier Neumann or Dirichlet Neumann, so this del U switches its position sometimes. And but if we have these data, for example, if we know this data on the boundaries, then we can determine this, or also like if we know this data, then we can determine this. So this is so one way either it's okay. And another thing is that we can write the integration by Bert's formula with both of these data. So we can write it down with Navier-Neumann combination or also Dirichlet-Neumann combination. So performing the integration by parts and deriving the integral identity, so which I will talk about soon, and so that won't be a problem. So this question is that, so now if we choose one of these Cauchy data, and then does this Cauchy data determine QBA uniquely? And here is our theorem. So it says that if you give two Cauchy data for two different set of QBA, so that's our notation. So QBA and Q tilde, B tilde, and A tilde. So then if you have this equality of the Cauchy data, so then that implies that Q equals to Q tilde, B equals to B tilde, and A equals to A tilde. So that means we recover scalar, vector, and matrix at the same time. And we do not face any gauge inference and so on and so forth. We have the global identification of all three coefficients. And we can do this with, so the one little remark that for this, so we are mainly interested in the recovering the second order tensor. So those we can assume that the regularity is all smooth and everything is nice at domain. But you can also do a little bit, so you can also choose like the Q is from L infinity class and this B is from W4 infinity intersection E prime. So we are choosing this, it's compactly supported, and A is from W7 infinity intersection E prime. So these indices are not that important. We can reduce it later, or so the whole point is that we are interested in recovering B equals to B tilde. So let's talk about what we know so far. So, so going back to the literature. So this is a polyharmonic operator. So minus a plus to the power m plus bx dot grad plus q. So here you see that you have only zeroth order and the first order perturbation. So you don't have any higher order perturbed terms. And then, so it's been known due to the result of Krupchik, Glasses, and Ullmann. So they showed that you can uniquely recover the full recovery of B and Q, the zeroth order and the first order. And it fails. So I just mentioned before that if you put m equals to 1, so m greater equals to 2 is important because for m equals to 1, it fails. So their proof shows that you can you have the full recovery of B and Q, and that opens up a lot of work. In particular, there are various articles about reducing the regularity of Q and B, considering the same problem in a like infinite slab. Also, the stability issue about Q and B, and also like considering the problem in manifold settings. So instead of Laplacian, so you have Laplace-Beltrami operator, and then you ask the same questions that whether I can recover Q and B, so as a scalar and only vector. But so then we looked into a different aspect. So in a sense that, okay, so we have only zeroth and first order. So if we add a little bit more, because as a perturbed term of a leading polyharmonic operator, so then can we recover those perturbed terms? So that means, so we are interested in higher order perturbation. Higher order means that higher than 1. So here, so that is the one model problem we looked at. And so we said that, okay, so this is my second order perturbation. So you can see that just AX Laplacian. So, and as usual, we have the first order and the zeroth order perturbation. So, and here you have m greater equals to 2. So then, so this is the work we started with Venki Krishnan, and we showed that if A is isotropic, then actually it's not so difficult to prove actually along the same line of proof of Krupchik and Glasses and Ullmann, that you do recover A, B, and Q. But the point is that you need to assume the A is isotropic, which was an important assumption there. And in fact, it's not about only second order. You can go actually, you can put also higher order, any other higher order perturbed terms. But the only condition is that, so if it's an even perturbation, so then we are assuming that this AK has to be it's a scalar or it's isotropic. And if it's odd, then we are assuming this is a first order, this is a vector coefficient. So BL is the vector and this AK is a scalar. So you can, if your operator is kind of this kind of formulations, or like if you put M is like the 6, 7, 8, whatever, so any higher number. So you can allow not only 2, but up to M by 2. So if it is 8, you can go up to 4. But the thing is that you can recover the lower order coefficients, provided they are in the form of either scalar functions or the vector function. So that means the question of really having a second order tensor is not given here. It's not mentioned here. It's not included here. So that was the next case we are looking for. And this is the work I did with Sombutha. So this is the first thing we did. So let's say we have a polyharmonic operator, so minus surplus to the power M. And we now consider a second order perturbed term. So that is AJK, DJTK. And we have first order and zeroth order. So then we showed that if M is strictly greater than 2, so then we can recover A, B, and Q. So this M strictly greater than 2 is very important. So here previously, at least in our old proof, so previously we are considering M equals to 2 also, like the biharmonic case. But here we are dropping the biharmonic case. So we need at least a 6th order operators for M equals to 3. And then only we can, we able to show that we can recover Q, B, and A. And I'll show you how, why it is, where we use that previously M greater than 2 and where we improve this time that we can also include the borderline case. So that means let's consider M equals to 2. So that means you have 4th order and exactly you have the second order perturbation, and that is not given by a isotropic matrix. So you have a general anisotropic matrix, and then can you recover that anisotropic matrix? So this is the new development we've made so far. So next step, so in solving that problem, so we have two different coefficients, so A and A tilde, so that the Cauchy data for two different problems for two different operators are same. So then, so it's not symmetric operator, so L star is not L. So we need to consider this L star operator for given L, A, B, Q. And so let's say this V solves this L star equation, and then U tilde solves this L, A tilde, V tilde, U tilde equation. And then you can show that, so you have this integral identity. It's just the integration by parts formula. So it's, you can start with any kind of Cauchy data that I mentioned, Navier Neumann or Dirichlet Neumann. And both of the cases, you can show that you have this integral identity. And then the next part is that, so we look for the CGO solutions. That's the standard technique for solving this kind of inverse problem. So we seek for this CGO solution, and this is the form. So this is a kind of very standard form. So we have this phi plus I psi h. So phi is the limiting Perturbed weight for the semi-classical Laplacian. So that because the characteristic equation for this by Laplacian operator is same. It's just the square of the characteristic equation for the Laplacian. So it's like the same limiting Cardinal weight will work for this Bi-Harmonic operator or even any polyharmonic operator. So you don't really see any change there. And the psi is the solution of the economic equation. So that means you need to have this mod of grad psi equals to mod of grad phi, and grad phi and grad psi, they are perpendicular to each other. So and then we have this remaining part, A0, A1, and R. So A0 and A1 are just some complex amplitudes, so which solve some transport equations, so that comes soon. And then this is the remainder part, R, so where we seek for the estimates, so that as the parameter small h goes to 0, so then this R goes to 0 in a suitable norm. So here is the thing. So as I mentioned, so this A0, A1 are the complex amplitudes. They're solving some transport equations, and R is the correction term. And so it's that this R2 semi-classical norm is order of A square. So that we just obtained, I just want to mention here. So here we put H A1 just to make sure that this R has this order of A square decay. Anyway, so here at the transport equation, so so the A0 solves this transport equation. So this grad phi plus I grad psi. So this is coming from this the weight and the phase. And then so this is, you can see this square A0, and this is the zeroth order perturbation of this the second order equation. So you see here a small observation. So if you have this AJK is a scalar matrix, it's a isotropic matrix. So that means that only J equals to K matters, and that also given by a fixed scalar functions. So then this entire term will be 0 because this A is outside, and this you have this grad of phi plus grad of I psi dot grad of phi dot plus grad of I psi. And then due to the fact that we have mod of grad psi equals to grad phi and grad phi dot grad psi equals to 0, so then we just end up with this transport equation. So grad phi plus I grad psi dot grad squared A0 equals to 0. So in particular, so if you have this isotropic matrix, so then your transport equation is a bit easy. I mean, actually it's really easy. And then you can solve these transport equations, and you can pick up those solutions to put it into this integral identity and to recover the coefficients. But if it is not, even it's a diagonal matrix, then it remains. And then the simple choices of A0, or the useful choices of A0 to put it in the integral identity becomes really hard. And so then, and also like we don't know at this point that whether we can solve these equations. And this is a homogeneous equations, and also this inhomogeneous part. So for A1, so the same equation. So with A1, but with a different right-hand side. So first we need to solve this A0. And then we plug this A0 here with a different operator, but let's assume that there is some non-zero term is coming here. So it's a homogeneous equation. And for that, we are seeking the solution for this equation with A1. So once we know A0 and A1, so then we'll plug it here, and then it's about the R. And so at this point, we assume that we can solve these transport equations, and let's see that what we can talk about R. So that means like whether this is justified or not. So that's the semi-classical estimate on R. And for that, we need the Cardinal estimate. And so that is the next thing you're about to say. So we need to find out the Cardinal estimate for, this is the conjugated operator. So this is the semi-classical Bi-Harmonic operator. And so you can write it down the same thing with you see this, the semi-classical Laplacian and square. So that means if you iterate 2 times the conjugated semi-classical Laplacian operators, then you can't get back for the conjugated operator for the semi-classical bi-Laplacians. And so this is the semi-classical Sobolev Swiss norm. So that's very standard. And then, so we seek for the Perturbed estimate with gain of two derivatives for the semi-classical Laplacian. So this is the known thing. And this is the gain of two derivatives. This is, I got it from the work of Salo and Zhao, Liu Zhao. And also I want to emphasize one more fact here. So we are considering this phi epsilon. So this is the convexified weight function. So that's why you get this factor h by root epsilon. So we need to use it because the idea is that we will apply 2 times this estimate on this operator. So that means we'll get a square by epsilon estimate. But this 1 by epsilon is important because we have a second order Perturbed term, so which is of order a squared. So to add that second order term, so we need to use this kind of this convexified Perturbed estimate. So as epsilon is small, so then h by root epsilon I can make it big so that the second order term gets absorbed. So if I don't have second order terms, so then I don't need the gain of two derivative, or even if I use gain of two derivative, I don't need to use this 1 by root epsilon factor. So if you do all those things, and then the adding the 0th order and the first order is easy. So you club it all together, and then you have this estimate. Sorry, this is one mistake. So there would be H4. So this is the estimate you get for this semi-classical conjugated L operator, LB. And then the standard technique we use. So then we use it to solve it the equation by using the Harmonic method to justify the existence of R, and also with the estimate that it enjoys that's order of a square. So then the main focus remains that whether we can solve the transport equations, and even if we can't, then what would be the way to solve that. So for that, so let's start with the phi and psi, which is phi equals to mu1 dot x and psi is mu2 dot x. These are the linear weight functions. And mu1, mu2 are some vectors from Rn, and the condition we need to have, so this mu1 and mu2 are perpendicular to each other, and this mu1, mu2 are also unit vectors. So I should have mentioned, I forgot it, but so mu1, mu2 are unit length, and they are perpendicular to each other. So then our transport equation for A0, so that becomes, so sorry, 1 minute. Perhaps. Can you see my screen?
Yes.
Oh, okay, sorry. So we have this transport equation. So it reduced to this transport equation. So if we choose this mu1 and mu2, mu1 dot x and mu2 dot x, the weight function. And then here we make another answer set that's A0. So we are looking for another CGO type solution. And this is the formulation we make. So this is the same phi and psi. So from the old CGO solutions, and then B and rho. So this B is the so new amplitude for these equations. And we assume that's, we seek that this mu1 plus I mu2 dot grad square B is 0. And this rho is the extra term or the corrector term, and that we are seeking that, of course, this is in H4, because it's a square operator, so that we want, but we want this L2 norm is small and its order of tau. So you say that for each fixed age, so we seek another CGO solution with another new variable tau. It's a small number, and this is our answers. And as tau goes to 0, we demand that rho goes to 0, where this B is amplitude, which solves the nice transport equations. And for that, again, we need to look for CGO solutions, and so that we can justify our existence of the solution. So in particular, so we do this change of variable. So from x to, you see this p, x, and x prime. So that's how we are writing. So basically thinking mu1 and mu2 as e1 and e2. And so in standard coordinate. So if we do so, so then this mu1 dot grad becomes del t, and mu2 dot grad becomes this dou s. And then I can realize this mu1 plus I mu2 dot grad as a d-bar operator. So that means I reduce the problem from into the d-bar operator. And for the d-bar operator, so there are known Cardamon estimates, and we can also so if we there's one more thing. There's a d-bar d operator and d-bar. So if I have mu1 minus I mu2 or minus mu1 plus I mu2, so then it would be the dj. So that's not bar. So this is the Cardamon estimate, so that we prove our our work. So if you consider this is phi is a harmonic function, so harmonic function in two variables t and x. So then so this tau square phi t plus, so this is the d bar square. So because we have here so mu1 plus I mu2 dot grad square. So it's not that we only need the Cardamon estimate for d bar, but d bar square. And for that, we have this kind of estimate. It's kind of H1 estimate. And also, as I mentioned, if you change the sign from mu1 to minus mu1, or here to mu2 to minus mu2, so for that also you can have this kind of L2 estimate, and with a gain of 1 derivative. So this is L2, and this is the kind of H1. And here you have this the factor tau, which is a small factor. So now we'll use this estimate to prove the existence of solution of the transport equations. So that's the part we do next. So this is the conjugated form. This is we denote by t phi. And so then we have this from, as I mentioned, so we have this L2 to H1, and then we can prove this H1 H minus 1 to L2. So which you use here, that is this estimate is required to get the existence with the right hand side V in L2, and then we have the solution U is in H1 semi-classical with respect to this new parameter tau, and it solves this. So tau U H1 tau semi-classical, that's because some constant C B, and this constant C is independent of tau. So once we have these A0 and A1, and then similarly we solve the A1 part. So once we have the existence of A0 and A1, so then we can plug everything into the integral identity, and then we'll seek for S tends to 0, and later T tends to 0, tau tends to 0. So this is the thing we do. So this is the determination of A equals to A tilde. So we have we have this integral identity. So this A minus A tilde part and B minus B tilde and Q minus Q tilde part. So here you plug the CGO solution for U tilde and V. And so this is the thing I just want to recall. So this is the U and V. This is the form we'll put here, and then we'll make A tends to 0. So if you do so, So we'll end up with this A naught and A naught bar. So this A naught and A naught bar, so they solve this equation I just mentioned like this. So this is the transport equations they solve. Okay, so we first we reduce this problem into this integral identity, and then we put the form of A naught and A naught bar. Next step, and then we make tau tends to 0. So if you do so, so then we end up with having B tilde and B, and where this B and B tilde solve this kind of transport equations. So, oh, sorry, this is, yeah, minus mu1 plus I mu2 dot grad. So sorry, so this grad is missing. So grad B whole square equals to 0, and mu1 plus I mu2 dot grad B tilde square is 0. So now we are in a relatively nice situation. So we know how to solve this transport equation. So we for B and B tilde, so we'll plug those solutions into this integral identity, and then we'll see what we can talk about A minus A tilde. So this is the next step. So we seek for B equals to 1 and B tilde equals to e to the power minus ix dot c, so which is a very trivial thing. And so which will immediately solve not only the square, but also like mu1 plus I mu2 dot grad B is 0, even at the first order it is 0, because we assume this psi is perpendicular to mu1 and mu2 both. So then we end up with simply the Fourier transform of A minus A tilde. And we have these factors, this mu1 plus I mu2 and mu1 plus I mu2 j and k. Then we put the decomposition for a second order tensor. So any second order tensor we can decompose into two parts. So one is f plus dv. So where this f is the divergence-free operator, divergence-free part. So that's for the each row and column. So we have this divergence-free conditions, and so this v1, v2, vn. So this is a smooth one form in omega tilde with the condition that it is 0 on the boundary. So I have this f plus dv. So if I put f plus dv here, so then the advantage is that if I do this integration by parts with this d, so then d will act on this one, e to the power ix dot c, because these are constants. So immediately one psi will come out, and then that will make things 0 because psi is perpendicular to mu1 and mu2. So I will only end up with the divergence-free part, that is f. So and then you choose that different choice of mu1 and mu2. So so not only so mu1 and mu2, but also minus mu1 and minus mu2. So you play with this, and then you also apply this another. So you can so by the choice of mu1, mu2 up to the full set, that mu1, mu2 up to this psi, the full vector, you can choose in a way so that this you can diagonalize this matrix F with respect to that particular choice. And if we do so, then we end up with having this relation. So this is the further deduction we do from this step, that the Fourier transform of F actually can be written as d psi as identity minus psi tensor psi by psi squared. And this is true for all psi is in Rn minus 0. So once we have that, so then we can invoke the Ries transform, and we can write it down everything in the physical space from the Fourier space to physical space. So we can have an expression for F. So this is the thing we do. So so in particular, we prove that in the X space, we can write that fjk equals to d sharp plus some half, and this is the symmetric gradient part. So del del xk of del d tilde del xk and del del xk of del d tilde del xk. So where there is a relation between this d sharp and d tilde, and which is nothing but just the Laplacian of d tilde equals to d sharp. So this d tilde is not two functions, and this d sharp is actually compactly separated function. So from there you solve this d tilde, and you can write it down f like this. So from here we can see that we have reduced our problem into two parts. So one is the isotropic part, so which we know how to handle. And here I have the symmetric gradient part, so which is also kind of nice because I know how to, now I can use the integration by parts again and again. So 2 times, so I can end up with having only d tilde. And then, so from those integral identities, it would be easier for us to conclude that d tilde and d sharps are actually 0. So here is the new expression for a minus a tilde. So what we get, so it has some scalar part that is d sharp. And so this is the vector part I'm mentioning, this is the symmetric gradient. And this is like d dx of vk and d dx of vj, where this v tilde is the gradient part of d tilde plus v. And the v is the old v that I have here, this v. Okay, so once I have that, so then you can prove this relation. So you plug it everything, and then as I mentioned that if you plug it here, this a minus a tilde, so this form, so then the isotropic part immediately vanishes because this mu1 plus I mu2 dot mu1 plus I mu2 is 0. So you don't see it there. So only the first order part will be there. This part will be there, but then you have the the solution of the transport equation for the b and b tilde. So that you need to use, and you do this integration by parts. And for that, after doing that, you will end up with mu dot v tilde x dx equals to 0. So, and this mu is perpendicular to all possible signs. So once you have that, so that is very familiar form. So we have, so from here we can derive this v tilde equals to grad p. So p is S2 function. And then from here, you can actually conclude this p is 0. So that is the thing I was mentioning, that next time you choose as e to the power minus ix dot psi and mu1 dot x. So such that this mu1 plus I mu2 dot grad v tilde is just only e to the power minus ix dot psi. But if you do the square, so then it becomes 0. But the advantage is that if you plug it here and then do this integration by parts once, so then you end up with having e to the power ix dot psi dx equals to 0. And from there, you can again conclude p is 0. So similarly, you apply the same technique. So for this D sharp, and to actually claim that you have A equals to A tilde. So that's a whole proof of recovering the second order tensor, and a very similar way you proceed by following this old paper that Krupchik, classes and Ullmann did. So because now you don't have that part, so you have only first order and zeroth order part, and you can show the equality of the B equals to B tilde and Q equals to Q tilde. So that means recovering all three scalar, vector, and the matrix. So I think I'm a little early, and so that's all I wanted to say. And thank you for your attention.
Thank you very much. Thank you very much to him for the very nice talk. Are there any questions or comments? Any questions or comments, please?
Okay, I have a question.
Please.
Yes.
Can you go back to the slide with this identity, orthogonality identity?
Why it is not moving? Here?
No, before that, there was A and B. Yeah, okay, I saw it. No, there was a difference of A, difference of B's, and.
Oh, okay, I see. This one, you mean?
Yeah, since you didn't write this operator in divergence form, that thing is not symmetric. Somehow, something bothers me here with respect to U and V. If you try to integrate by parts, going to get derivatives of A and A tilde. No, I'm not saying that I see that it is wrong, but somehow I expect some kind of symmetry that I don't see.
So we first we make the difference from this U and U tilde from this equation, and then as we are choosing V from L star, so we think that that will take care of that part.
Oh, so this is solution of a different equation, of star equation, okay.
Yeah, this is it's not the same equation.
It's not the same with B tilde. Okay, I guess I missed the star there. Okay. Thank you.
Okay, are there any other questions or comments? Any other questions or comments?
I have a question.
Please, please.
So, why is the critical case like the half of the sort of, so you have Laplace to some power m, and then you have basically Laplace to m over 2. I mean, why is the m over 2 like the critical case? Just
okay. So the point is that, so because, for example, if you ask me, okay, so for example, if you ask me that, can I add a third order? So let's say you take this m equals to 2 case. So you have this Bi-Harmonic operator. So then if you ask me to add a third order term, okay, whatever the third order term,
right,
and then proceed in a similar way. So then I can't, because that's a problem I have with the Carl-Lewin estimate. Because you see this, so when we seek the Carl-Lewin estimate for the Bi-Harmonic operators, it automatically becomes this the square of the conjugated Laplacian. Now, so you already know the estimate for the Laplacian. So that is with H, and that is optimal. And now if you iterate one more time, so you get H square term here. Now, if you have a third order term, so that will give you an order of H term. And with that order of H term, you cannot absorb by this order of H square. So that is the main problem that it's kind of, if you follow this particular method, so that you really cannot go beyond m/2. So if you iterate for m times, so that would be h to the power m. All right. So if you go a little bit below than h to the power m, so h to the power m minus 1, so then you cannot absorb it into the Carl-Lewin estimate to write it down the estimate for L. So that kind of forces us to consider up to this m/2. That's the problem with this Carl-Lewin estimate. Yeah, but I can give one more comment. So like instead of considering this Laplace square operator, so that's the Bi-Harmonic operator. So you can also consider the operator kind of like dx1 to the power 4 plus dx2 to the power 4 up to dxn to the power 4. So which has no cross term. So only the fourth order derivative. So there is no d4x1 x2. So in that, but the problem with that operator that it is not rotational symmetry. But in that case, you have a different Carl-Lewin estimate, and where actually you can allow a little bit more. So that's one just side comment I just want to mention. But with this polyharmonic operator, I think that is the problem.
So the this linear Carl-Lewin weight, I mean, you apply only linear Carl-Lewin weights that work for like the second order operators. Maybe is it possible like a different weight? I mean, since it's like a different operator now.
Actually, you can also choose the logarithmic weight. That's not a problem. But I think, but you cannot improve this h to a square. So, so for if you do one more perturbation, so for the Bielaplacian, you always end up with a square. And actually, there's I think that's the work by Kripchuk, Klassas, and Ullmann. So they considered the Bi-Harmonic operator in a, and they considered the inverse problem for the the partial boundary data. No, so here we consider the full boundary data though. So, and there they actually consider this Cardamom estimate with a logarithm weight function. So as you were mentioning, that those are not linear weights. But the thing is that if you, but you can call, so this phi would be different, but the power of h, which matters in terms of proving the the decay of the remainder term, which is very useful to get the identity. So there you don't get any advantage. So that's my point.
Okay, thanks.
Thank you very much. Are there any other questions or comments? Okay, if not, thank you very much, Tuhin, for the very nice talk. Thank you very much, everyone, for coming. Thank you very much.
Okay, thank you very much.